Imagine waking up one morning, you check your phone, and navigation systems across an entire continent have just vanished. Well, been completely overwhelmed, actually. That is exactly what happened when a massive, unexplained GPS dropout hit all of Europe simultaneously. In this explainer, we're jumping straight into a really thrilling scientific investigation into that exact event. We're tracking down a space mystery that goes way beyond anything we've ever seen before. So let's just dive right into the data.
And look, I want to be clear right off the bat, this wasn't just some minor, everyday glitch. Professor Todd Humphreys, who's a huge name in navigation over at the University of Texas at Austin, along with his student Zach Clements, they dug into the data and found 75 days since 2019 where these incredibly strong disruptions took place all across Europe. Looking at what they found, Humphreys literally said, unprecedented. The world has never seen this before. And you can totally understand their disbelief. Receivers from way up in Svalbard down to Spain all saw this massive drop in signal-to-noise ratio at the exact same time. They uncovered this continental-scale disruption just sitting there, hidden right inside publicly available tracking data.
Okay, so where was it coming from? Initially, the researchers naturally thought about a ground-based source, right? Maybe a massive high tower in Kaliningrad, since that's a known hotspot for electronic warfare. But simple geometry and, well, the curvature of the Earth immediately ruled out a ground attack. A tower signal can only reach so far before the Earth literally curves away. To hit receivers across all of Europe simultaneously, the source had to clear the horizon for every single station at once. To do that, you need an altitude of at least 1,200 kilometers, so the culprit was pointing straight up. It had to be in space.
So if the interference is coming from space, you might be wondering, could it just be the sun? We know major solar flares can absolutely scramble GPS globally, but we can systematically debunk the solar theory pretty fast. Natural solar flares build up slowly and they span a really wide range of radio frequencies across the whole sunlit side of the Earth. But the actual data here? It showed these really abrupt bursts confined to a highly targeted, super narrow 5 megahertz slice, and it was exactly where GPS operates. Plus, the disruption was consistently centered strictly over Europe, so the sun was officially off the hook. This was without a doubt coming from a satellite.
Now, before we actually go catch our culprit, we really need to understand the rules of the game here, the incredibly precise math our devices are using every day. When your phone tries to find your location, it listens to global navigation satellite systems, using a precise 4-step process. First up, the satellite broadcasts its position in space. Second, it sends the exact timestamp of when that signal left. Third, your phone's receiver calculates the time it took for the signal to arrive. And finally, fourth, it multiplies that transit time by the speed of light to get your exact distance from the satellite. Once you lock onto 4 of these satellites, boom, you know exactly where you are on the planet.
But what's truly mind-bending here, and I mean literally staggering, is the insane precision required to make those calculations work. 3 seconds. That is the maximum amount of time a satellite's onboard atomic clock will drift over 1 million years. Think about that. Because these signals are traveling at the speed of light, an error of just 100 nanoseconds, which is almost nothing, throws your location off by 30 meters. Your phone obviously doesn't have an atomic clock inside it, so it has to constantly solve complex algebraic equations on the fly to correct its own time using these hyper-accurate signals from space.
Wait, actually, it gets even wilder. To calculate your position, the satellite first has to know exactly where it is. It relies on ground stations to tell it. But the Earth is constantly shifting, right? Tectonic plates are always moving. So how on earth do ground stations know exactly where they are? Get this. They use quasars. Ground stations map the Earth's continental shifts using incredibly bright radio sources from literally billions of light years away. These quasars act as fixed, absolute reference points. So essentially, to know what street you're standing on right now, we are quite literally navigating by the ancient light of the stars. How cool is that?
And the physics don't stop there either. Just to keep you on the correct side of the street, your phone has to silently account for general and special relativity every single second. I mean, without that, your position would drift by 11 kilometers in a single day. It also has to correct for the Earth's rotation during the tiny fraction of a second the signal is flying through space, not to mention all the delays caused by the ionosphere and local atmospheric weather conditions. It is just a stunning, beautiful display of incredibly delicate math.
But here's the catch. Because it travels 20,000 kilometers from space, the signal reaching us down here is shockingly fragile. It arrives at a power of 10 to the negative 16 watts. That is a tenth of a quadrillionth of a watt. To put that into a bit of perspective for you, trying to detect that signal is basically equivalent to trying to see the light from a standard 50-watt household light bulb from 2 entire Earth diameters away. It is insanely, unbelievably quiet.
Which brings us to a really crucial point. As one expert put it, it's kind of like yelling over someone whispering. And that is exactly what jamming is. Because the navigation signal is so incredibly quiet, it is terrifyingly easy to just overwhelm it. All a jammer really has to do is broadcast a stronger noise at the exact same frequency, and those delicate navigation signals are completely drowned out. Your phone's receiver simply can't hear the whisper anymore.
So bringing it all back to our big mystery, was this satellite jamming just an accident? Perhaps a random hardware glitch or an amplifier just got a little too hot? Well, the data revealed a pretty chilling pattern that we can call the business hour anomaly. These interference events, they didn't happen randomly. They were clustered almost exclusively on Tuesdays, Wednesdays, and Thursdays, right during standard European business hours. As the researchers pointed out, random hardware failures do not stick to a midweek work schedule. This decisively proved human intent and malicious design. Someone was definitely doing this on purpose.
So the hunt was truly on, but working backwards from a signal in space is incredibly difficult. You can't just, follow the signal strength. So the researchers used a really clever geometric filter. There are over 15,000 active satellites up in orbit, but because this interference hit all those European stations at exactly the same time, the suspect had to be above the horizon for all of them simultaneously. That single geometric constraint eliminated over 98% of the satellites instantly. And when they factored in the requirement to be visible during multiple events on different days, they narrowed that vast field of suspects down to just 14 possibilities in the geostationary belt.
Now, one of those 14 was a satellite operated by Algeria. On paper, it was the perfect suspect. It had an orbit visible to all the stations, and public documentation showed it actually had a transmitter in the exact frequency band they were investigating. It looked like a slam dunk, but deeper analysis proved it was a false lead. When researchers looked closely at the data from receivers tracking this specific Algerian satellite during the events, its signal-to-noise ratio dropped exactly like the normal GPS signals did. So it wasn't the attacker. It was just another victim being jammed by the real culprit.
And with that, the trail went completely cold for months. The standard GNSS receivers only provided one simplified sample per second, which, to be honest, wasn't nearly enough resolution to pinpoint the source of a tiny 3-second burst. The original data was from 2021, and the initial tip-off didn't even come until late 2024. By September 2025, they took the investigation public to the global scientific community at the Institute of Navigation conference. It basically became this massive crowd-sourced hunt. Finally, in February 2026, an email arrived completely out of the blue. 2 stations had captured exactly what they desperately needed: the raw, high-resolution digitized radio waves of the actual event.
The mathematical breakthrough that finally cracked the case wide open relies on something called time difference of arrival, or TDOA. Because they now had raw data sampling millions of times per second from 2 completely separate tracking stations, one in Amsterdam and one up in Trondheim, Norway, they could measure the microscopic difference in exactly when the jamming signal hit each location.
And what was that microscopic difference? Exactly 139 microseconds. The signal reached Trondheim just 139 microseconds before it hit Amsterdam. This tiny timing difference allowed the researchers to draw a warped geometric surface in space, a hyperboloid. Because the raw data was so incredibly high resolution, the margin of error was mind-blowingly tight. We're talking just 5 meters thick, stretching across tens of thousands of kilometers of space. The culprit was trapped directly on that exact geometric surface, leaving them absolutely nowhere to hide.
From there, the researchers systematically tested every single possible satellite's orbit against this hyperboloid, and only one object perfectly matched the math. The culprit on mast was Cosmos 2546, which is part of a Russian early missile warning constellation. This military satellite sits in a highly elliptical Molniya orbit, basically a path that allows it to fly really high over the northern hemisphere and just linger there for extended periods. It aligned with their exact data to within 200 meters, which is well within the public tracking data's margin of error. And independent teams in Europe have actually since verified aspects of these location findings too.
So the data clearly points to the source, but what's the motive here? There are actually 2 competing expert theories right now. The first theory suggests these are periodic tests of a massive jamming capability, deliberately run slightly off the main frequency just to test the hardware without, causing total global chaos. The alternative theory is that these aren't jammers at all, but rather highly covert specific communications messages.
By using these protected frequencies, a military avoids the risk of their enemies jamming the signal simply because doing so would completely destroy the enemy's own navigation capabilities. Pretty clever, right?
But honestly, no matter the motive, let's pull the lens back for a second and look at the true stakes of what we're talking about in this explainer. Navigation systems aren't just about ride-hailing apps or getting directions to a restaurant. They are an invisible, deeply fragile utility that underpins virtually every single piece of our modern infrastructure. An orbital jammer threatens aviation, global shipping routes, the precise synchronization of our global financial systems, cell tower timing, and even power grids. A disruption from a constellation of satellites covering this much of the globe could instantly affect hundreds of millions of people.
Which leaves us with this final, pretty provocative question. Are we prepared for a day without space? This investigation proves our dangerous dependence on incredibly weak, easily overwhelmed signals from orbit. While some countries are just now beginning to build out resilient terrestrial backups, things like fiber optic timing cables and magnetic navigation systems, much of the world remains highly vulnerable to a major outage. The threat from space is very real, and the data shows it is already active. So what do you think? Are our critical systems ready for a day when the stars go dark? That is something we all need to be seriously thinking about. Thank you so much for exploring this data with me today. Stay curious and keep questioning the systems around you.